Cronius back here again, and today we're going to be working on some JavaScript algorithms inside of Leetcode. So sorry it's been a few days since I last streamed. Things have been kind of crazy over here. I have been studying, but a little bit more on my own. So, I thought after taking, quite a long break, we would maybe get back to things and kind of work on some problems together. Now, this problem we're about to look at today, I'll admit, unlike the last few times, I actually did look at ahead of time, and in solving it, it was deceivingly simple to solve, but it was primarily because I'm just unfamiliar with the terminology that was being used in this problem. So I thought it might be a good idea to go through it so you can kind of see where I kind of misunderstood what was going on, and we can work through the two possible solutions to this problem together to kind of understand. So today's problem we're going to look at, and if you are, if you had done this stream today if you'd done this algorithm today on June 7th, 2022, you would have gotten Leetcode 1332, which is remove palindromic subsequences. Now, if you're like me, you have no idea what the heck a palindromic subsequence actually is. I know what a palindrome is. A palindrome is something, that you can, when you read forwards and backwards, like the word radar in English, you get the same word back. But subsequences was something that was a little new to me, and I actually kind of misinterpreted that to mean substring, which apparently turns out is a very, very different thing than a subsequence. Before we get too far ahead of ourselves, let's go ahead and read through the problem description and kind of understand what the problem is asking us to do, just like we always do. All right. You are given a string S consisting only of letters A and B. In a single step, you can remove one palindromic subsequence from S. Okay. Don't know what that means. Well, I thought I knew what it meant initially, but it turns out I was wrong. But we'll keep reading the problem to see if we can clear it up a little bit. Return the minimum number of steps to make the given string empty. So in this case, we are basically trying to eliminate all the letters in the string by what would appear to be finding palindromes in the minimum number of steps possible. So whenever I see a string and we're talking about some sort of string manipulation, the first thing that comes to mind personally is two-pointer. Because two-pointer is a very efficient way to divide and conquer. It's basically a technique of divide and conquer that allows us to quickly tackle array-like string solutions in a performant manner. There are variants of two-pointers, like for example, I don't know if there's a technical term for the algorithm, but there's one I particularly like to use, which is the endpoints, where you start at the ends and go inward. And then there's something called sliding window, which effectively is you fix a pointer one point, and no pun intended, that's terrible English, and you move the other pointer until a certain condition occurs, and then you adjust the first pointer and then move the second pointer back from that first pointer. So you're effectively creating a sliding window across the array. And we'll run into problems like that probably eventually on the stream, so it'll make more sense. But just from a first intuition's sake, when I see this problem, and when I had started this problem, immediately I started thinking through a two-pointer approach. Okay. A string is a subsequence of a given string if it is generated by deleting some characters of a given string without changing its order. Note that a subsequence does not necessarily need to be contiguous. Yeah, I'm going to be honest. I had no idea what this meant. I thought that a subsequence was literally a substring. So let's say, for example, let's say you have a string AAAB like this. I thought what it meant was, okay, if you remove this, this is a subsequence. This is not a subsequence. And let's finish the problem, but I'll kind of explain where my confusion came into play and kind of what they were really intending in this problem. A string is called a palindrome if one that reads the same backwards as well as forward. And I gave the radar example earlier. I think most people are familiar with what palindromes are in general. But the real key to this problem and what threw me off was this paragraph about the definition of a subsequence. So let's do something a little bit more simpler. This is too abstract to me. Let's think about what are subsequences in like more plain English words. So an example of a plain English word may be something like electronics, right? So this is an English word. We're typing and using them right now, right? So substrings of electronics might be elect, Tron, if you're a big fan of Tron Legacy and those movies like I am, because I'm a huge nerd to be honest. Or maybe, I'm trying to find words in here and this is not the easiest one. But you get the point, right? Like those are subs, or even, it doesn't even have to be English word, or something like wrong, right? That's a substring because they're contiguous and they're small pieces of the overall string. A subsequence, which is not the part I understood, is basically a set of characters maintaining the order but not necessarily contiguous. So a subsequence of electronics might be something like, let me see if I can do a real one, tick. So basically I take TIC, so that is a substring, but it's not necessarily a contiguous substring. So it is considered a subsequence. I think this problem is pretty tricky. I think what this problem is doing is trying to make you think about the problem rather than the solution, which I am guilty of. I always am guilty of wanting to immediately go to the solution without thinking through the question. And I think while it seems like this problem may have, maybe made some people a little angry because it doesn't really necessarily follow the format most standard Leetcode questions ask, it is good in that it is actually a thinking problem, because if you actually understand and you talk to the person asking you this algorithm, for example, what a subsequence really is, once they give that away, it becomes pretty obvious what the solution is with a little bit of thought. All right, so now that we've kind of given a description of what subsequences are versus substrings and palindromes, we'll go ahead and delete this. So let's talk through the two solutions that we possibly have for this problem. So we know that, and before we do that, let's go ahead and talk through the constraints. The string is somewhere between 1 to 1,000 characters, and every letter in the string is either an A or B, which is exactly what the problem constrained. There are some examples here. We can go through them, but I think the examples weren't super straightforward to me, I think, until I got to example 3. But let's kind of talk through what's going on here. So let's say, for example, and in fact, I think example 3 is pretty much the critical one in this scenario. So let's say, for example, we have a string of BAABB. So the question is what is the minimum number of steps, or I should say, what are the minimum number of steps to take to empty out this string, given that we can basically remove one palindrome subsequence from this? And what this means is basically I can pick any sequence of characters, not necessarily in order, and remove it. Then after that point, how many more steps do I need to take to empty it out? So let's look at BAABB. So if I'm looking at this, the first thing I see is I could eliminate this, right? So I could pick my subsequence, which is also a substring in this case, as BAAB, right? But actually, I could also pick a subsequence, BAA, skip this B, and get this B. So these are equivalents, right? This is a substring and a subsequence. This is just a subsequence. But since we're just talking about subsequences in this problem, not substrings, these are equivalent. So what is the net result after we remove both of these? Well, the answer is, if I remove BAAB from BAABB, I'm left with B, which is the last character. If I remove BAA, skip the 4th index, and go to the 5th bit, well, what am I left with? Well, I'm still left with a B. So the answer is B. So in this case, what we end up getting is it basically takes 2 steps to eliminate this. Now, let's think a second. The trick to this problem is that only 2 characters are allowed, A and B. That is a very, very, very important clue. And let me explain why. Suppose you have a string that's something like this, right? So this is just a random string, right? And I'm making up something kind of off the top of my head. What we know at this point is we're allowed to basically remove a palindrome's worth of characters with no real repercussions, right? We're allowed to do that once, and then we have to say, okay, how many steps are left at that point to remove the rest of the characters? So by inspection, we could already tell this is not, like intuitively by inspection, we can tell this is already not a palindrome, right? And the reason why it's not a palindrome is that BBBBB and BBB are never going to be the same value. So we know at minimum 2 steps, right? So even if we remove a palindrome from within this, we're still going to have some characters left that we're going to have to remove. So we already know that the min in this case is going to be 2, but let's see if we can prove that. So if I'm looking at the sequence of strings, I'm probably going to have to, yeah, we're going to have to grab quite a few characters, and they're definitely not going to be in contiguous order because it's not a palindrome. If it was this, for example, BABBA, well, BABAB is a palindrome, so I just picked the entire thing, and the answer is 1. If the string is empty, which it isn't in this case because the minimum string length is 1, then it would be 0 because the string is already empty. So now we're solving for the case where it's not empty and the string itself is not a palindrome. So if I look at this sequence, and this might be tricky, bear with me because I picked a really long one. So let's see if we can get this right together. Looking at this, I probably am going to want to do some combination of those A's and try to grab at least one of those B's at the end. So let's find a subsequence together that makes sense here. So in this case, I'm going to pick B, I'm going to pick A, I'm going to then pick A again. So let's put dashes by the ones we picked so this is a little bit clearer what's going on. So I'm going to pick A, I'm going to skip B, I'm going to skip B, I'm going to skip B, I'm going to pick A. So that's 4 A's, A. I can't take that A, right, because I don't have a matcher left. So if I take that, then it's never going to be a palindrome. And so at this point, let's kind of look at what's left. So we have 5, 6, 7, 8 B's, right? Well, what can I do in this case? If we kind of go back in time, what we can actually do is do. Let's see if I'm going to do this. Let's see if I do this correctly. It's trickier. It's almost trickier to do this intuitively than get to the answer we'll get in a minute. But let me see I'll give you a hint at what I'm arriving at. What I'm going to tell you is that after this step, there's 1 palindrome left to remove. And what I'm going to actually tell you, and this is the spoiler, is the max number of steps is always going to be 2 removals. It's going to be either 0 removals, 1 removal, or 2 removals. So, but let's show that. Let's see if from this one we can figure out what the 2 removals is, because it's kind of a fun problem, right? So let's see if we can do this in easier way. So what if we take, let's see. So we know at minimum this is going to have to be all right. Let's see if we can figure out a subsequence palindrome from this. And bear with me if you're watching. I know it's going to be painful because you've probably already figured it out, but let's see if we can get it together. So let's see. A B B B A B B B A B B B. So if I take out the A and I put in a second B and I throw in, let's see, if I throw in another B, okay, so I have 4 B's and 4 B's here. Let's see, trying to think here real quick. So we have 4 B's here, 4 B's there. And I have 5 A's in the middle. What am I currently left with? I would be left with an A and a B. That doesn't seem like it would work because AB is not a palindrome, right? ABA or BAB would be a palindrome. So let's think about this a second. All right, so let's think about this. All right. I probably could struggle hard. Let's pick some. I hate to lose here, but let's pick something that's slightly easier. So let's pick one that's a fewer characters, something like this, right? So obviously this is not a palindrome, so we know we need at least 2 steps to clear out this string. So if I'm going to pick a subsequence here that I can eliminate, I'm going to eliminate something like, let's see if we can find one that makes sense. If I do BABAB, so basically I pick character 0, character 1, I skip character 2, and I take these, then what am I left with? After I take the subsequence, not substring, I take the subsequence, what I'm left with is just a single character A. Well, A is a palindrome implicitly because A reversed is still A. So in this case, the total number of steps is 2. So the real trick to this problem is it turns out that if you can pick an arbitrary order of characters, let me back up. By picking a subsequence, which basically allows you to pick any characters you want as long as they're continuous, but not continuous, they're in order but not continuous, you can effectively reduce any string with 2 characters in maximum 2 steps if you're allowed to take out a palindromic subsequence. And the reason why is that you can pick a set of characters in order such that you basically eliminate everything but the remaining palindrome in the string. So, and you can kind of see that if you look at the 3 examples that problem 1332 gives. So for example, the first one is ABABA. Well, I don't need to do any work on this one, right? Because ABABA is already a palindrome, answers 1. And we'll write a quick 2-pointer algorithm that kind of shows you how to basically figure out if it's a palindrome or not. It's actually pretty straightforward, and it's an often solution for these palindrome style problems. Example 2 is ABB. Well, in this case, the only palindrome we have that's a subsequence would be BB, right? Because BB reversed is also still BB. So we're left with A, which is another count, so then 2 steps, right? The last example they give is, and this is the one that's supposed to really make you think, is BAABB. So what is a subsequence palindrome I can pick from this that will basically result in only 1 step being remaining, or 1 step remaining? Well, as we discussed, if I pick B, A, and then either the 3rd or 4th index B, I'm going to be left with B in either case, so the answer is still 2. So our function should either return, well, to be safe, even though the constraints don't ask for this, it should return 0 steps if the string is empty. It should return 1 step if the entire word is already a palindrome, or it should return 2 steps because we know that once we pick that subsequence, there's going to be 1 palindrome left in the word and we can eliminate it with a second try. So that's the trick in this. This fooled me hard, and it will make me probably think a little bit closer when I'm looking at these string style problems. But let's go ahead and talk through solutions, how we would actually solve this now that we kind of intuitively understand what's going on. So for solving palindromes, you really have 2 approaches. You can reverse the string and compare it to itself, and you can kind of determine whether it's a palindrome, right? So, because if you reverse a word to compare it to the original word, they better be the same, otherwise it's not a palindrome. So you might ask, well, what does that have to do with palindromic subsequences, right? Like we were just talking about basically finding a subset, well, yeah, a subsequence in this case, and removing it, and then we would basically find out if we had nothing left already or we need to do at least 1 more. So it turns out that we can just go ahead, basically if it's not already a palindrome and it's not an empty string, then we know the answer is 2. And the reason we know the answer 2 is, again, like we said, we can pick a subsequence such that there's basically forced to be only 1 palindrome left, which might be a single letter, might be 2 letters. There's like actually quite a few different combinations of results depending on the length of the string, depending on what you pick, but the resultant is that you will eliminate the string always within maximum 2 tries. So let's solve it the first way. Now, the first thing we should ask is, what is the cost of doing a string reversion palindrome check? Well, so then the question is, okay, what do we have to do to reverse a word or a list or an array, depending on what language you're in? Well, to reverse something, you have to go to each member of that list or array, and you have to touch it and do something, or in this case, reverse. So from a big O perspective, that means that as the word gets larger, you're going to have to touch more and more and more entries as the number gets larger. That scales n, because the amount of work you do is scaling with the size of the list. So using a reversal algorithm is O of n, complexity. And it's always going to be full O of n because you're not going to do the O of 1 comparison. So comparing two primitives is O of 1. Well, not really, actually. It still could be O of n now that I think about it. I'm actually trying to remember for string primitives in JavaScript whether it actually is an O of 1 action, because those primitives have unique... That's a good trivia question. I don't remember the answer to that. Obviously, if you compare numbers, that's O of 1, right? But when you're comparing string primitives, I do believe it's still an O of 1 operation, but I'm going to go check that, and if I'm wrong, I'll come back and talk about it next time. So let's go ahead and implement the reverser algorithm. So you could do your own reversal using two-pointer. Let's not do that for this one, because the preferred solution is two-pointer end-to-end in this case, which will be scenario 2 spoilers. So let's just use built-in array functions, in this case in JavaScript, to kind of show what this would have been. So, and of course, if you're in an interview and they want you to do the reverse, you'll see how to roughly do the reverse in a moment when I do implementation 2 with 2 pointers. All right, so first thing we need to do, now if you want to make this work for all cases, is you check if s.length is equal to 0. Or if you want to do a shortcut in JavaScript, you can actually just remove this entirely and do this. Because an empty string coerced in an if statement in JavaScript, or really for any Boolean logic, is going to be what's called falsy, or false. So if the string is empty, then, well, there's no work to do because it's already empty, we return 0. There's basically no work to do in this case. It's already an empty string. So that's the first case. And to be honest, we can actually keep that there for the second way of doing it, because irregardless, if the length of the string is already 0, you're not doing any algorithmic work anyways. Your algorithm is literally just returning 0 count. All right, so let's assume now we have a string that is not of length 0. You know, it's at least of length 1 or to 1,000 per the constraints of the problem. So in this case, we're going to need to reverse that. So what we're going to do is we're going to define a new variable called sRev, because naming is hard, where s_rev is s reversed, or we could even just call it reversed. That's probably better, to be honest. And we're just going to take s, and it's not as straightforward as you think, because it's a string, right? So we're going to have to split it. Actually, I'm trying to remember if there's a reverse, if string prototype actually has reverse. I don't think it does, because I honestly don't reverse strings very often in my day-to-day, but let's check. So we're going to check array or we're going to check string prototype, and we're going to see if it has a reverse. Yeah, so you see here, so my intuition was correct. So you'll see there's an array prototype reverse, which is what I was about to use. But let's look at this. You know, it's always good to get second opinions. Let's look at this Free Code Camp article, which I'm a huge fan of Free Code Camp, and see if there's an array. So yeah, this one's using split reverse join, which you literally just saw me doing. So that's case 1. This is just a for loop. Yeah. Okay. So yep. So yes, this is the way to do it. So good. There is no reverse on string prototype, and we confirmed that. So what this line of code does in line 7 is it takes a string, it splits it into an array in between each character. It's going to reverse that list. So if it's radar, it becomes radar as a list of R-A-D-A-R. And then it joins it back together basically with no, delimiter is probably the wrong word, but basically things in between them. So it's basically just going to smush the array back into a string. So we're just going to generate reverse here. And then what we're going to return is we're going to use a ternary to keep it. You can use an if-else in this case, but I think a ternary is sufficient. So what we want to check is if s is absolutely equal to reversed. So basically, if the word is already a palindrome, then we know one subsequence removal will clear the string, right? Because the entire thing's a palindrome, so we can take it at once. In this case, it's a substring and a subsequence because it's contiguous, and it's a subsequence because it's a collection of characters that is basically you're collecting them in some forward order, but they're not necessarily a contiguous block of them. So if they match at this point, then we know that we can do it in 1. So if this is the case, we're going to return 1 because there's one action to be done. If they don't match, then we know we have to at least remove one palindrome first, and then we should be left with 1, in which case we have 2 actions to do. So this should solve the problem. We're going to run it against a simple test case of ABB. So in this case, for ABB, how many steps would it take to clear this list? I'm going to pause 5 seconds and then I'll explain the answer. Okay, so in this case, the answer is 2. So what subsequences can I pick from this? So I could pick AB, so I could pick indexes 0 and 1, or I could pick AB, which would be indices 0 and 3. Either way, if I pick 0, 1, or 1 and 0 and 1 or 0 and 2, I'm left with B, which is a palindrome. So I have 2 actions left. So in this case, what I'm expecting to see is that we return 2. And that's exactly what we see. We return 2. Now I'm going to go ahead and submit this to run the full test suite, but this should work. And sure enough, it does. We succeed. Okay, so this is the first solution. But it's kind of expensive, right? Because you're always going to have to at least run through the entire list. There's no chance you exit early because there are cases in palindrome algorithms, which we're about to talk about, the more common approach that's more performant potentially, where you might know 1 or 2 or maybe even 5 characters in, yeah, there's no way this is a palindrome, like we should exit early. So there's no point in going through the entire list if you already know that it's not going to be a palindrome through the algorithm. So we're gonna do the other case, which will save you time in a lot of instances, because it's probably likely, and again, it depends on your data set, that you probably don't have all palindromes. Now, if you had all palindromes, then there's actually really no performance difference between these 2 algorithms. I mean, there probably is, depending on the implementation of V8 you're using, how basically the browser implemented V8. But that's way too far to the middle, and that's kind of pointless for this conversation. So let's go ahead and do algorithm 2 for this, which is what I would use personally. So we're gonna look at this in a second way. So what we're going to do here is we're going to leave this first line, right? Because this first line is still good. Like I just said, if the string is empty, it's empty. There's no work to do. That's fine as is. So what I want to do is I want to define a function, and this function is going to basically ask, is the word a palindrome? I cannot spell palindrome. Wow, this is embarrassing. This is what happens when you do a stream at 12 in the morning. Excuse me. So we're gonna create a function that checks to see if the string is a palindrome. It's gonna take s, which is a string in this case. If I was using TypeScript, I would do something like this, but we're not in TypeScript right now. We're just in JavaScript, and I'm just gonna use an arrow function in this case because it's fine. We're not worrying about implicit. This is fine in this case. What we're gonna do now is we're gonna apply 2-pointer approach. And we're going to use an algorithm for palindromes that will start from one end and the other. And what we're going to see is if the value at the first pointer and the value at the last pointer in the string are basically the same. And we're going to work our way inward. And the way we know it's a palindrome is that as we move these 2 pointers closer and closer in together, if all the letters at that pointer in the list, sorry about that, a pointer in the list are the same, then we know that it's continuously a palindrome. If at any point they're not the same, they're different letters, we know that we already don't have a palindrome and there's no more work to do. We can exit it because it doesn't matter what the rest of the characters are at that point. We already know that that violated the rules of what a palindrome are, so we can move on with our lives. So that's exactly what we're going to code here. So we're going to start out, we'll go ahead and create, we're going to call this pointer A. And pointer A is going to sit at the beginning of the list, or index 0. And then we're going to let pointer B sit at the end of the list, or in this case, s.length -1. Because remember, in JavaScript, arrays are 0 indexed. So the first index in the list is 0, and therefore the last index is the length of the list -1. We have to offset by 1 basically to 0 index versus 1 index to the list. All right, so now that's done. We can't just operate on the string. It's a primitive, and you can't really iterate on it necessarily the way you would think the way we want to in this case. So the easier thing to do, and unfortunately this does use a little bit of memory, but you're already using memory above by doing string.reverse, is we're going to define an array, and what we're going to do is we're going to split the array into, we're going to split the string into an array of characters. So if you have radar, for example, it becomes this, right? So that's what we've done here. All right. Now, and then finally, what we're going to do is we're going to create that loop because we need to basically keep iterating through the string, moving those pointers until either we find out that it's not a palindrome because the letters don't match, or the pointers cross each other, which means that all the characters matched, therefore the word is a palindrome. All right, so let's code that. So very typically in two-pointer algorithms, you'll see this while loop. So while pointer A is less than pointer B, so basically while they haven't crossed yet, while the left pointer hasn't crossed the right pointer in the list, what we're going to do is ask, okay, is the value in the array at pointer A not equal to the array at the value in the array at pointer B? So in other words, is the left pointed value not equal to the right? If they're not, this means we're not a palindrome, and I can return false because we're done. Because as soon as, again, I detected that mismatch, we're done, we move on. Otherwise, we're golden. So let's move the pointers further in and check, and then we're going to loop again. So in this case, we move the left pointer up by 1 and the right pointer down by 1. So we're getting closer, 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 and closer. If we get to the end of this loop, basically we find no matches, then we're going to return true, because if we get through the while loop and it never fails, then guess what? It's a palindrome. All right, so we've got our palindrome, and this is, by the way, the very, very common solution to using two-pointer approach to determine whether a string or a list of characters is indeed a palindrome. All right, and that's all we have to do for that. So then the next question is, okay, so that's great. We created a two-pointer function that determines whether it's a palindrome. Now what? That doesn't give us anything because right now we're returning void. We just defined a function in a function. All right, so the last thing we're going to do here is we're going to finish with a ternary again. So what do you think, given that we have a function that determines whether a string is a palindrome, what should we do at this point? And think back to how we solved the previous problem with a ternary return. So, like we discussed previously, if the word is a palindrome, we're done. It takes one time because we can remove the entire word on our try and we result with an empty string. So, if the string S is a palindrome, then we know we're done. It's one step and the count is 1. If the word is not a palindrome, that means we, in the background, would extract a subsequence that is a palindrome, and we would be left with one more palindrome to remove, in which case 1 plus 1 is 2. So this is very similar to the above, but instead of just reversing and doing a comparison, which theoretically I could have also defined this function and stripped out the guts and did the reverse, I'm just doing a two-pointer approach, and this gives the opportunity of what we call an early exit in order to try to optimize the number of steps that are be taken, given that we don't know much about the data set. Because if the data set doesn't have a lot of words that are already palindromes, this is great. This will save us time. Again, though, if the data set has a lot of words that are palindromes, this saves us no time because you still have to iterate through all the characters to determine whether it's a palindrome. We can't make assumptions. We have to, at minimum, check every single letter to make sure it meets the criteria of a palindrome before we can determine said word is a palindrome. All right. So long story short, let's test our test case again. And again, we're accepted. And if we run the test, we will see that yes, indeed, it passes the test suite. So let's review what happened here. So the problem said, okay, given a string that only consists of 2 different characters, and you're basically allowed to strip out a palindrome of characters that aren't necessarily continuous, how many steps does it take to clear out the string, to basically remove all the characters from the string? The key for problem 1332, again, is to realize that a subsequence is not a substring. A substring is a continuous set of characters that can be extracted, like we discussed, from the word, and then let's just pick another one. Let's say, for example, computer. We know that a subsequence of computer might be something like put, or yeah, let's just say put in this case, right? That's a substring. But a subsequence is a selection of characters, but they're not necessarily contiguous. So a substring of computer would be cut, which is index 0, and then these two, I think these are indexes 4 and 5, but I'm just doing quick math here. So 4, 5, so that's a subsequence. So again, the trick here is that basically, as the user, I can pick a random set of characters, and because there's only two characters, there's only so many permutations that can exist in said string. And the trick just so happens to be that, yes, the answer is, if it's not already a palindrome, I can pick enough characters such that I guarantee only one palindrome is left in the word, so the max answer is always 2 if it's not a palindrome. And that's it. So I'd argue this is a little bit of a trick. I don't think you would get this if you hadn't seen this before, but sometimes a lot of algorithms is seeing strange things that you don't think about day to day, which is what this was for me. And then you think in the future, are they asking about substrings or subsequences? Because they are very distinct things that have very big implications on your solution. All right, that's all the time I have today. Thanks so much, and I'll see you all next time. Take care.